In this problem, we have a 6-inch diameter pipe that is 600 feet long and is carrying water at an elevation of 80 feet, position A, to position B, which is an elevation of 120 feet. We are told that the frictional stress between the liquid and the pipe walls is 0.62 pounds per foot squared. Determine the pressure change in the pipe and the lost head. And so in this system, we're going to assume that the water is incompressible, and of course the pipe diameter is going to be constant. We have an elevation change here, so that is 40 feet. We need to calculate what? We need to calculate the pressure change in the pipe and the lost head. So this is going to be a Bernoulli's equation, but we've got a little bit of a twist with this problem because we are told that the lost head is related to the frictional stress between the liquid, and they give us a value for the frictional stress. And so we may not be used to calculating what the frictional losses are through that method, and so what we're going to have to do is we're going to have to go back to our fluid mechanics textbook and figure out how to calculate head loss based on the shear stress between the fluid and the pipe walls. So if we do that, we find that the shear stress is equal to the density of the fluid times the hydraulic radius, where the hydraulic radius is the cross-sectional area divided by the wetted perimeter. All right, and then times the head loss, and then that is divided by the length of the pipe. And so what we can do then is we can rearrange that equation and solve for the head loss, and that is fairly simple to do. All right, so that takes care of calculating what the head loss will be. That's the stress that's given to us. The length of the pipe is given to us. We know the density of water, and we can calculate the hydraulic radius. So let's start assembling all of our other given information that we're going to need. Let's put in our let's treat position 1, and for the Bernoulli equation I like using 1s and 2s. You can use A's and B's, but I'm going to use 1s and 2s, and so I'm going to set position 1 as the datum, as the baseline, so that's going to be an elevation of 0, and so that makes Z2 equal to 40 feet. I'm going to use an average density, a nominal density of water of 1,000 kilograms per meter cubed. We've got our shear stress. We can write that in terms of American or SI units. Diameter, length, we can calculate a surface area, cross-sectional area, and the perimeters, and of course are constant due to gravity. First thing I'm going to do is calculate the head loss, and I'm kind of skipping ahead, but it's just a simple algebraic equation now that we've got it. The hydraulic radius is the cross-sectional area divided by the wetted perimeter, and so we're going to assume that the pipe is completely full. We don't have a partially filled pipe, and so which just wouldn't make sense given our flow geometry here. And so our hydraulic radius is 0.038 meters, and you can see that that reduces to the diameter over 4 for a circular cross section that is fully wetted. So what we can do now, of course, is calculate what the head loss is, and this head loss is going to be what we're going to substitute into our Bernoulli equation for solving for the pressure drop. And so the head loss, this should be in length units, and it certainly is. It's 14.53 meters. We can convert that to feet to 47.671 feet. So now we can finally use the Bernoulli equation and calculate what the pressure difference is. And so our Bernoulli equation, we're going to apply it from position 1 to position 2. So I have P1 over rho g is equal to V1 squared over 2g plus Z1. So this is our energy at position 1. I'm going to account for a head that can be added, for example, by a pump. head that can be lost, and that's what this is due to friction. And our general equation, also you can account for head that's extracted, and this would be if you had a turbine or expander. But of course we don't have that, and so that's going to go to 0. And that is equal to the energy that we'll have at position 2. And so that's P2 over rho g, V2 squared over 2g plus Z2. All right, so we can go ahead. Let's bring a schematic over here so we can figure out what's going on. Remember what's going on. Our point 1 is the lower inlet. The velocities. The velocities are the same because we have a pipe of constant diameter. So the velocity terms are going to cancel out. Z1, we're setting that equal to 0. So Z2 is going to be 40. So make sure you keep that straight. And it turns out we don't need to know how the pipe is angled. We don't need to know if this is a 45, 60, 30 degree angle, whatever that is. The total length over 40 feet, we don't need to know that angle. We just need to know the final height. And so we have this term canceling out, the head added, head extracted, this velocity, Z1 is equal to 0. So all we're left with when we simplify our Bernoulli equation is our delta P. Our delta P is, which will be P1 minus P2, because we'll keep that positive, right? That is equal to Z2, and then what's left, plus the head loss, and then we multiply that by rho g. And so that is equal to 38 psi or 262 kilopascals.